All right, here we go, class. How's it going? Today is the first day of your figmented notes of me not being here, talking through the walls, or spying on you through all the cameras in this room. Kind of weird, but kind of happens. Anywho, today is the first day of your forces and Newton's law unit. You should have gotten a calendar that kind of maps out the next 2.5 weeks. So the hope is you can see the pacing and the guide whether I am here or not. You should see that your homework tonight is looking and finishing up the math lab that you're going to get here in a little bit. It is also going to be doing some reading out of the textbook and a couple problems practiced on them. Now, a reminder, you should have a hard copy of the textbook if the online stuff wasn't working for you already. Otherwise, on my website, it does have the PDF version of the entire textbook. So in this unit, Forces of Newton's Law, you will see a textbook folder, and in there it'll have the textbook PDF file you can open with anything to read from. So, with no further ado, follow along with that calendar as we do go over the next couple of weeks. So that if I'm here or not, you know what I expect of you, and you can get your questions asked, follow along with the book. Question for today is, what is a force? What is force? I'm going to give you a minute or two to look it up. If you don't know it, you better look it up on your phones, in the textbook, with the person next to you. There's absolutely no reason you shouldn't know this answer. And then we're going to move on. So something, go ahead and stop it. You guys go ahead and work. Find the answer. Go. All right, my hope is that you have found that answer. With the sub pausing and stopping it, you're able to talk about what you thought force was. We've learned about this before. I have taught the middle school curriculum. I know I say that a lot, but I've taught a lot of different places. And I know we should know what that is. Supposedly, it's in your requirement that I could have started here 2 weeks ago, 3 weeks ago. But we started with acceleration. So let's move into that. Well, what is force? Well, to me, without forces, the world would be very boring. We talked about how acceleration, right? Last unit was what makes things amazing, what makes things fun. It's why we do stuff, because it's changing a speed or a direction, which is fun. And here, without forces, it would be boring. Because forces make us know what acceleration is. It is also talking about mass, stuff that's there. So let's take a look. What is a force? Couple ways. The book defines it as this. Definition-wise, it is any influence that tends to accelerate an object. Well, the best thing about that is you should already know what acceleration is. You should know that acceleration is the change in a velocity. And you can do that in two ways. You can change its speed or change its direction. So a force causes something to change. Yes, it is hard. It takes force to cause something to change. But it also says an influence that tends to accelerate an object. And an object, any object that actually thoroughly exists, must have a mass. Right? Otherwise, it doesn't exist, because the mass is the stuff that makes it up. So when I start to take a look at it is, well, how I define it, yes, that is the words for it. I tend to think of it more as an object of a push or a pull affecting an object, because a push or a pull tends to accelerate or change the motions of an object. What you should know, before we get into really defining it in terms of mathematically, is that it is a vector quantity. You should know what that means. When we study what a vector is, it means it must have a number, it must have the unit, and it must have the directional piece. If it does not have a directional piece, it is not a vector. And in this case, if you don't know what direction the force is affecting you in, it is absolutely pointless to even say there's a force there. So we're going to be drawing a lot of pictures, defining where are the forces going or coming from, so we know how it's influencing the object. Now looking down here, here's what you should know. You should know that force, if you were to mathematically do it, which once again I am lazy, you can use the words from up here, but I like using the mathematical equation. It says the same thing in my brain. It says that force is the F, equals a mass, which is the m, right? Force equals a mass times an acceleration. If you remember from middle school, we defined that as Newton's second law. So Newton's second law is actually the mathematical definition of a force, which is, once again, force equals mass times its acceleration. Now, too often there's a lot of stuff affecting a problem. Not often are you only affected by one force. When you're sitting in your seats right now, you are affected by more than one force when you are sitting there, whether you know it or not. And therefore, we need to start figuring out the total force that is affecting an object. Because you are sitting in your seats. You are sitting stationary. There are forces that are affecting you, yet you're not moving. So if there's a force there and that tends to accelerate an object, yet you're not moving, what does that mean? And that's because we need to figure out the total force on objects. Because the total force is what causes you to actually move, okay? Or accelerate, or change what you're doing. And that's where this bottom part comes into play here. Because, nerd-wise, math-wise, it says F net. F net means total force. This sigma math equation, the beautiful looking E here in front of the F, what does that mean? It means add up all your forces. If you're adding up all of your forces, what does that mean? It means you have found a total force. And so we're going to be drawing pictures all the time required for this unit because there are a ton of forces that affect something. And in doing that, we are going to come up with the net force. Because the net force is, yes, the sum of all forces, which is why something moves. Because you are being affected by a lot of forces right now, and they just so happen to cancel themselves out, which is why you are not moving in your seats. Not that you're not being affected by a force. And so we need to start drawing pictures and figuring out, well, what is really happening? Let's add up all of my forces affecting an object before I decide how it's going to change and accelerate that object. Okay? So that's forces, basic definition of forces. But let's start looking at the units for force. Okay? Well, if we know that a force is a mass times an acceleration, that means that a force, mass, so what is mass measured in? Mass is measured in kilograms. Yes, it can be in grams. For the sake of this equation, it must be in kilograms. Okay? Well, let's look at units. You know I love looking at units. So we have force equals, well, a kilogram times, what's the units for acceleration? You better know a meter per second squared. Once again, if it's not a meter per second squared, it does not work for this equation. So units you must have are kilograms for your mass and meters per second squared for your acceleration. Now, in doing that, you'll get a kilogram meters per second. So the units that can be used, yes, you can use a kilogram meter per second squared. But to me, that looks like vomit. It is disgusting. I do not like it. And you know what? In the science world, we are wicked lazy. Because none of us are going to write that over and over and over again. So what happened is Sir Isaac Newton came around and he's like, hey, I found this out, so let's name it after myself. And so he calls this a Newton, which is represented then with just a capital N, which is why we see it here. So you need to know both. You know that it can be written as a kilogram meter per second squared. Blah, disgusting. You're not going to see it that way much. You should still know it. You're going to see it written as a Newton because, oh, it's so much easier just to write an N. And I am lazy, so that's what we do. Okay? So that's how we get to its units. Now we have some things down here, some pictures you will see, and we're going to start calling these force diagrams. If you're reading your textbook, they may call them free body diagrams. Why? Not really sure. But they're usually interchangeable. Either know the force diagram or free body diagram. Basically what it's saying is draw me a picture of every single force affecting an object. and tell me what direction it's in. So if we look at this, I tend to use boxes. We have our first box up here, right? So here's the box. Let's just say it's eraser on the chalkboard. I don't know. Okay? And these arrows are very key because these arrows tell me the force. So here it says, here's how big the force is, and it's happening in that direction. Once again, the length of the arrow tells you the size of the force. And the directional component tells you what direction it's happening in. Well, over here we must have another one. So we have the length of the arrow, and now you can see its direction. And if we look at those two pieces, we can see, hey, this arrow here is smaller than this one here. Therefore, this force must be smaller than this force. Okay? Because the length of the arrow determines the size of the force. Length of arrow equals size of force. Okay? So our length of our arrow become very important to tell us the size. And the arrow tip is telling you where and what direction. Arrow tip says the direction of force. So our pictures become very key. Remember last year I said you must always draw a picture and then retell yourself what you know to even attempt the problem. This is why. Because in this unit, you have to draw a picture, otherwise you're going to miss stuff, and then retell yourself what you know. And if we can set that up as the model you always do, you're set up well for success in this class and other math or science classes where the problems are pretty hard. I know that these problems are not going to be easy, but I think you can do them as long as you teach yourself how to think through them. So let's take a look at my next box. Okay? I'm going to skip the circle one. I typically don't do anything with the circle because circles you can't see the sides. You can't see the X direction. You can't see the Y direction very well, and so I don't. Literally every single thing I do, if it's making a person or a car or an astronaut or a snake, I am going to draw my free body diagram of that of a box. Because I can then see the vertical components of the box and the horizontal components of the box really easily. And I am a horrible drawer, so this helps me out. Okay? Now, if I'm looking at here, I want to look at what happens to my total force. Okay? So I can see right now that I have a really big arrow going to the right. Let's put a number on it. We'll call this 10 newtons for fun. Okay? I can also see that I have a really little arrow, about half the size, so we'll call that 5 newtons going to the right also. On the back side, I can see that I have another arrow going to the right, which looks similar to the other one, so we'll call it 5 newtons. And last but not least, I have an arrow going to the left, and I'm going to call that then -5 newtons, primarily because it's going the opposite direction of my other ones. So if I want to claim that to the right is positive, I'm going to say to the left, is negative. Okay? So if I wanted to add up this total force, we should be able to look at the picture and say, where's my object going? Well, I hope you can see that this arrow here and this arrow here are roughly the same size but in opposite directions, so they cancel each other out. Whereas then the rest of my arrows that are left are pointed to the right. So you should easily be able to see that this object is going to the right. If you wanted to actually calculate the forces, what we could do then is add them all up. My net force. Well, it is I'm going to start on the left-hand side. So I have a -5 newtons plus 5 newtons plus 10 newtons plus 5 newtons. You add that all up, you will get, well, negative 5 plus 5 is 0, plus 10 plus 5, we should get a total force of 15 newtons. And if you notice, it's in that positive direction, which means it better be going this way, which is what our picture showed. So that's why it's so important, because from our free body diagrams, or from our force diagrams, we're going to be thinking through all of the forces that affect my object. So that's called free body diagrams. We'll get into more of those, talk about more of those tomorrow, and how to think through a problem. Okay? But to really understand force equals a mass times an acceleration, we've already talked about acceleration last unit. We've made sure you know exactly what it is and how important the directional piece is. And so now we really have to start talking about mass. Because in our weird, odd society, we interchange words that don't make any sense to interchange. And one of these is weights and mass. And so we need to figure out, well, what is mass? Mass, it is the quantity of matter in an object. You also might know it as the stuff in the object, or the matter that makes up an object. Okay? How do we measure it? Well, you can measure it in grams or anything on the gram scale, but for the sake from here on out, we're going to use kilograms because my equation demands kilograms right now. But we really have to look bigger than that, because then we start getting into Newton's laws, which we learned about the second one, I think it was MA. We start getting the other ones, we really have to be more specific to even what mass is. And what you will see that mass measures inertia. Awesome, that is a sweet nerd word, inertia. What in the world does inertia mean? Inertia, in the sense of what you know and what we probably can understand better, is considered laziness. It is the object's resistance to change. So mass can also be called inertia. It's a measurement of inertia, excuse me, which is the measurement of an object's laziness. Okay? The more mass an object has, the more lazy it is. Well, what is laziness thing? I hate being called lazy. So what does that really mean? It means its ability to resist change. Okay? Think about that. Something that has a lot of mass, a semi-truck. If it's parked, sitting still, is it going to be super easy to change what it's doing? I mean, it's really lazy. It has a lot of mass. It's sitting still. To change it would mean to get it started. Can we walk up behind it and just easily push it? No! It took a lot of force. It's really, really hard to move because it is going to resist our change because it has a lot of mass, which is the measurement of inertia, which is the measurement of laziness. Think of something else. If you were here, I would throw some paper at you right now. I'm throwing it at the class, and there's nobody in here, so it looks really weird. Paper ball was super light. That's why it was super easy for me to move it, because if it doesn't have much mass, it's not going to have much inertia, which means it's not very lazy, therefore it's really easy to resist the change. I mean, it's really easy to cause it to change what it's doing. So mass is the measurement of the stuff that's in you, and it measures the inertia or the laziness of an object. Okay? Which is super important, because when we start looking at understanding what gravity is doing, we have to understand sorry, my brain stalled there. We have to understand a couple key pieces. One, being that as an object falls to the ground, we know that it's going to accelerate. We know that gravity exists. So we have to start talking about, well, what is gravity? Then we talk about mass, and we talk about acceleration, but specifically, what is gravity? Well, we know that on Earth, all objects will accelerate at the same rate regardless of its mass, because we are so close to Earth's mass. We know this acceleration is 9.8 meters per second squared toward Earth. Maybe some of you have heard of it as negative 9.8, and I would say pay attention to the negatives and the positives, because really it's only a directional piece. So I think the best way to say it is toward Earth, because depending on your problem, you could say it's positive or negative. Correct? So we know it accelerates the same way towards Earth. We did the demo last unit and showed you that a piece of paper and a book and a basketball and a calculator all dropped at the exact same rate and hit the ground. We see over here my simulation is not working, so I apologize. There is an elephant and a little mouse. We drop them off the same height building at the exact same time. They're going to hit the ground at the exact same time, because what's the only thing affecting them? Gravity. And what is the acceleration caused by gravity? 9.8 meters per second squared toward Earth. So if you look at here, which one, so that's what's going to happen. Which one is going to exert more force when it hits the ground or when it lands? Well, then we have to look at the real equation. Force equals mass times acceleration. If we look at that, we can see that, well, there's going to be a really huge mass. Sorry, erase that here. My elephant's mass is really big, but my acceleration is the same. But in doing that, I have to have a really huge force when the elephant hits the ground, because if my mass got bigger, so did my force. If we're looking at the mouse, then my mouse is going to have a really little mass. Just a little guy. Okay? But its acceleration is the same. I can make it the same size. Therefore, we are going to have not as big of a force of the mouse when it hits the ground. So clearly, even though, in this case, my accelerations towards Earth are going to be the same, because my masses are different, my forces when they hit the ground are different. So yes, they hit the ground with different force, however, they're accelerating at the exact same rate of 9.8 meters per second towards Earth. So keep that in mind. Remember that as we go on from last unit. But this brings me to the really annoying saying that we have. Because we have things that are called LA weight loss. Well, we'll show you in a second. Weight is actually a measurement in pounds, which is a measurement of force. And so weight is a force. Specifically, it's your force caused by gravity on the Earth. And so instead of saying LA weight loss, it really should be LA force of gravity loss. Which means they're doing nothing to monitor what's happening inside your body and the stuff that's there. Because stuff is mass. Mass is measured in kilograms because it is the stuff that's there. Whereas weight is a measurement of force. And those aren't the same. So we have Weight Watchers once again, and if we really call it the same thing, it should be the force of gravity watchers, because weight is the force of gravity affecting your mass. Nowhere in those titles did it talk about the stuff, the matter that's in you, and therefore we're looking at completely wrong stuff. Welcome to the English language, into America, we are looking at stuff that doesn't matter. Who cares what your force is? That's what gravity is doing. I want to know the stuff you're putting in your body and eating, that is the mass. But nowhere in here does it talk about mass. So let's really look at that again, okay? If we know our Newton's second law, it's F equals ma, which is force equals mass times acceleration. If we know on Earth our acceleration towards Earth is 9.8 meters per second squared, we can then rewrite it like this. The force of gravity that's affecting something is its mass times 9.8 meters per second squared, right? Because that is your force pushing into Earth because of your mass times by the acceleration of gravity affecting you. This is weight. Weight is is a force. Weight is the force of gravity on your system. So what we really should be doing is writing, when we talk about weight, we should be writing it like this. Why? Because weight is the force of gravity, and the force of gravity is a mass times the acceleration of gravity here on Earth. Well, that also means that this acceleration of gravity here on Earth, called 9.8 meters per second squared, people call that little g. Yes, it's just a little g. Okay? And so little g, what that means is that we can now represent the acceleration of gravity as little g. And we can rewrite our problem as weight equals the force of gravity, which equals the mass times little g. Finalizing us to this equation here. Weight is a force, mass times an acceleration. So weight is the force, weight is the force, and mass is the stuff. When you go to a new planet, you will weigh something different because gravity is going to affect you differently. Your stuff, your mass, your matter doesn't change. You don't all of a sudden make up different properties that you're made up of when you go to the moon. No, you weigh less because gravity affects you less. Your stuff didn't change. And we got to look at the stuff that's there, the mass, okay? So that's how we get to the equation and use Newton's second law to find weight, because weight, once again, is the force of gravity, which is a mass times the acceleration of gravity here on Earth. So it's really using force equals mass times acceleration to solve for your weight. One and the same, okay? So once again, mass, measured in kilograms, it's the amount of stuff or matter on you. It does not depend on gravity. Weight is measured in newtons or pounds because it is the force of gravity on your system caused by an acceleration of gravity we know here on Earth of 9.8 meters per second squared. And just to help you remember, this is a nice nerdy little song, so here you go.
Mass versus weight. To measure for an object, they're not the same, let's all see why. To determine the mass, we use a balance to do it. We use a scale to measure mass. Measured in grams or in kilograms. It's all about how much stuff the object has. So you can see, mass and weight aren't the same thing. Weight is the measure of gravity's pull. In contrast to weight, mass tells us how much matter, how much matter the object has. Mass, measured in grams or in kilograms. It's all about how much stuff the object has. Massive weight there, huh?
All right, so you can see, whoo, I got really loud on me here. Kind of a fun little nerdy video that really starts to show the difference between those two things, and it gets stuck in your head and you remember it way longer than you want to, but that's a good thing. So mass and weight, very different. To really understand Newton's law of gravity, because we talk about gravity so often, and too often people do think it's your pull towards Earth. And I would say, no, it's not your pull towards Earth. Yes, gravity does affect you towards Earth, but gravity is not defined by its pull towards Earth. The universal law of gravity, which you should already know at some point in time, talks about how every object in the universe is attracted to every other object that has mass. Because what gravitational force is, it's an attraction force between any two things that has mass. So if you look around the room and find anything that has a mass, yes, the person sitting next to you, there's an undeniable fact that you have an attraction to them. You're sitting in class right now, my projector is attracted to you. And you are attracted to my projector because you have mass and my projector has mass. Therefore, there's an undeniable force that attracts you to. A little bit less than the size of the Earth, because the size of the Earth, mass of the Earth is pretty huge. But how does this really work then? This is a big, big equation here. It specifies the force, which is F, right? Force. Big G, which we talk about as being the universal gravitational constant, which I would always give you is this big, nasty number here. You'll never have to memorize that. I will give it to you. What does it equal? Well, it equals the mass of the first object times the mass of the second object divided by its distance apart squared. So remember, D is basically the distance of separation. Yes, there'll be some calculations we will work with this, but mainly I want you to know the main concept behind it. Why is this so important? Well, because if you look, the equation for gravity demands the attractional force between anything that has mass. You need at least two objects that have a mass and they're attracted. I am attracted to the stars right now. I am being pulled by gravity to the stars right now. Why? Because I have a mass and the stars have a mass. The reason I don't notice it as much is because our distance apart is so huge. And even though our distance apart is so huge, if our distance is squared, it makes that distance feel even bigger. And if you divide by a really big number, your force is very small. It's still there, it's just small. And so if we look at the two main things that affect it, one that affects it is the mass of the objects. Clearly, the more mass you have, the more force you have. Because the forces are multiplied together. The masses are multiplied together. So the more mass, the more force you're going to have on an object. Which is why you are pulled so greatly to Earth, because Earth's mass is so ridiculously huge that even if you're just a little bit, the mass of the Earth is so huge it doesn't matter. And that's why if we're relatively close to the Earth's surface, we are going to have an acceleration caused by gravity of 9.8 meters per second squared towards Earth. Regardless of mass, a semi and a piece of paper are going to fall at 9.8 meters per second squared because the Earth's mass is so ginormous, it doesn't matter what the other mass is. But probably the most important indicator, because it is a distance squared that's on the bottom, is the separation between them. And here's where I think of it as a relationship. You can have a long-distance relationship. It is hard. The force can still be there. The attractional force can still be there. My wife and I dated for 3.5 years, long distance. I was in Minnesota. She was in Arizona. I got lucky and it worked out. She got stuck with me. But if their attraction is still there, it's just really hard to maintain. It takes a lot of work. There's not much force. Whereas if you get to see somebody every single day, all the time, your distance is very small. That attractional force is huge. Or has the ability to be. I mean, the Earth is not very big in terms of our solar system planet-wise. Yet, You have the most attractional force to it because your distance is very close to Earth, and your distance to Saturn is not. Saturn is way bigger. Jupiter way bigger. Except you're just further away from it. And our distance is our number one impactor of how you're going to experience the force. Okay? Because it is squared, meaning extra, extra, extra important. So how does this work? Well, let's take a look here, and then we'll be done for the day. I've talked way longer than I thought I would here. If you have a politician on Earth, and the same politician now out in outer space, who's going to experience the greatest gravitational force towards Earth? I hope you're almost screaming on your chairs because you want to answer this. If he is on Earth, his distance is going to be, can't even say it. His distance is going to be very, very small to the Earth, right? Whereas when he's out in outer space, his distance is much further away. Based on that, if you're farther away, you have a lower force of gravity affecting you. The politician is going to have a greater force of gravity affecting it. Even though their masses are the same, my masses aren't changing. The distance, the separation is huge. Okay? Looking over here on this example, now we have an equal distance between the moon and equal distance between the Earth. So my distances are the same. Which direction is going to have the stronger gravitational force? Towards the moon or towards Earth? I hope you say towards Earth is going to be really, 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 really big. Why? Because Earth's mass is far bigger than the moon's mass. Therefore, the force of gravity towards the moon is going to be very little, and the force of gravity towards Earth is going to be huge. So it's going to get pulled towards Earth with your total net force. Yes, there's two forces affecting it, but if you were to add them up, it's going to be a greater force towards Earth. Therefore, it's going to start accelerating or changing its motion towards Earth, which is the reason force comes around. So, enough of me yakking for today. What I would like then is you're going to have your mass lab. You should have roughly, 30 minutes to finish that. You're going to be reading through that lab. You're going to be using the mass scales to measure the mass of stuff, or you can use the triple beam balances that are out as well. They're going to be calculating the mass on Earth. You're measuring the mass on Earth. You're going to calculate its weight on Earth. That's force. And then you're going to calculate its weight or force on the moon. You're probably going to need to figure out the acceleration of gravity on the moon. You can look that up. Awesome. Keep your job with the utmost respect, and I will talk to you tomorrow.